I'm reading the book Computer Systems: A Programmer's Perspective, and in the first chapter, they address Amdahl's law. And I've encountered Amdahl's law in my undergraduates in its relation to concurrency and parallel processing, but they address it as a general law in optimizing any process. So the important sentence that really jumped out to me, it was this one here. This is the major insight of Amdahl's law. To significantly speed up the entire system, we must improve the speed of a very large fraction of the overall system. So let's kind of decompress that a little bit. I have some diagrams I prepared to try to explain why that is the case and illustrate it. So let's start with this diagram over here first. So we have Amdahl's law, which is expressed as the speed up of the entire process is in relation to two terms, alpha and k, whereas alpha is the proportion of the process that you're optimizing, and k is the amount of speed up that you obtain by optimizing that portion of the process. So a good example here would be like if we have a process that takes 100 seconds to run. This is a completely serial process, no parallelism involved, just 100 seconds from start to finish. And say you identify a function in that process that's actually taking up 50% of the runtime. And so you're like, okay, that's a huge chunk of this process. I'm going to select that for a candidate to optimize. And you work really hard at it and you get, say, like a 4x speed up. So that would be this worked example here where alpha is 0.5 and k is 4 for 4x speed up. It's just some simple arithmetic here. You end up getting 1.6% speed up of the entire system. And you might think that sounds kind of small, and it is. You put all this effort in to get a 4x speed up on half of the process. You would think that that would have a huge impact on the total process. But basically, even if you had infinite speed up of this entire section of the process, you still have 50% of the process that you're not optimizing. And so even if this went to zero, this whole section went to zero, which is what this worked example is up here, you're still going to have 50 seconds remaining. So you're bounded by that, and you can only ever get a 2x speed up if you're focused on just half of the process, optimizing half of the process here, which makes sense intuitively, but when they present it in an equation like this, it might seem kind of like what's going on there. So this work example, we're optimizing half of the process. K is set to infinity because we just say it's completely optimized. So this whole term goes to zero, and then you end up seeing that you're bounded by 2. And if I pop back out here, this blue line here represents that bounding. So you can see how as you improve the optimization of this process, the speed up that you get is bounded by 2. So you can see that right there. Let's go back over here. Another example might be, say, okay, you expand your horizons. You're like, okay, I'm going to address 75% of the system, and I'm going to optimize it fully away. Well, you can't get rid of this quarter. So the best that you can ever do, even if you optimize 100% of this thing away, is to get a 4x speed up. And then say you address the entire process and you speed it up by 10x. Well, that's obviously just going to be a 10x speed up of the entire process. So these are just some worked examples that kind of illustrate some data points on that graph. But I do actually want to show the 3-dimensional graph of Amdahl's law. So I plotted the surface in red here, and this is a 3-dimensional graph. So we can see the z-axis here is A. So this is the amount of the process that we're actually spending time optimizing. So I have some plots here for 50% and 75% and of course 100. So let's go ahead and look at that. So from top down, y is the amount of speed up that we get. X is the amount of speed up of the sub-component of the process that we're putting effort into optimizing. And so you can see those limits that we spoke about before, where, let me zoom in a little bit more. So you can see this blue band here is limited by 2, and the green band ultimately is limited by 4. So it'll approximate 4, but it'll never be able to exceed it. So, playing around with these graphs and understanding Amdahl's model a little bit more, let's go back to the text and revisit this sentence. This is the major insight of Amdahl's law. To significantly speed up the entire system, we must improve the speed of a very large fraction of the overall system. Amdahl's law is applied in the context of parallel computing to understand how much performance you can get out of parallelizing a given process. Some workloads are inherently parallelizable, embarrassingly parallelizable, in which case the amount of parallelism you throw at the problem, you'll get a linear relationship with the amount of performance speed up that you get. Whereas some workloads are inherently partially serial, in which case you will be limited if you no matter how many parallel processes you throw at the problem, you'll be limited in your performance improvement by the amount of that process that is inherently serial.